Well, welcome everyone to this session of radiation separating fat from fission. Please introduce yourself in the chat. Tell us where are you joining us from, if you have any role within CCL or any organization you're representing, and what brings you to this webinar today. So I am going to pass it on to Jim.
Okay. Hello, everybody. Today's presentation is being put on by the Citizens Climate Lobby Nuclear Energy Action Team. Now, some of the people on the call might not be from CCL, so I'm gonna start by telling you what we're all about. CCL and the Nuclear Action Team. CCL, or the Citizens Climate Lobby, is a large grassroots climate organization that has over 200,000 volunteers and has chapters in almost every congressional district. Their focus is on decarbonization. In particular, they support policies that put a price on carbon pollution. The Nuclear Energy Action Team is a subgroup within CCL that has three main objectives. The first objective is to reach out to the nuclear industry and seek their support for carbon pricing, which generally would benefit that industry. The second objective is to provide guidance to other CCL members on how to speak about nuclear to legislators and others. And finally, the third objective is to be a source of expertise and information about nuclear for CCL members. Today's presentation is an example of the things we do in support of that third objective. Okay, just some logistics here. The way we're going to handle comments is that we're going to wait till the end of the presentation. And as Solimi may have said, you put your comments in the chat and, we'll sift through those and, call you up to ask your question. So the speaker today is Dr. Gerry Thomas, a molecular pathologist with an interest in radiation-associated cancer. She has spent the last 2 decades of her career helping to debunk the myths that surround the health effects of radiation, in particular, those related to nuclear power. This talk will focus on what we know about health effects from exposure to low levels of radiation, including the health effects of disposal of nuclear waste. And with that, I'll turn it over to Dr. Thomas.
Thanks very much. I'm going to share my slides. Hopefully you'll be able to see these in a minute. Can everybody see that okay?
Yes.
Yeah. Okay, lovely. All right, I'm going to try and keep this to about 40 minutes or 45 minutes, so you've got plenty of time for questions at the end. Let me see if I can get this to advance. It was going very well, that's it. So this talk is going to cover the background. Hang on a second, let me just get rid of that. It's going to disturb me otherwise. It's going to cover background information and the definition of terms that we use to describe radiation effects. And we use lots of different terms, and that can sometimes be very confusing for people. I'm going to stress the importance of dose in determining health effects, and then we're going to look at the health effects of Chernobyl and Fukushima. And then we'll briefly touch on radiation doses from nuclear waste, because that's another thing that people seem to be worried about. Then we are going to try and put some of those public health risks from radiation into perspective. And I'll give you some links to more detailed information that you can easily access for further reading at the end. So firstly, for radiation to cause damage to cells, it's got to come into contact with them. And that mechanism of contact depends on the type of radiation, whether it's a waveform, for example, gamma or X-ray, or a particulate form, as in alpha or beta, i.e. a helium nucleus or a beta electron. Radiation exposure can be external or internal. And the internal route is particularly important when we talk about particulate radiation, but we'll talk a bit more about that in a minute. There's one important thing that people tend to forget in that the dose of radiation falls very rapidly with distance from the source. This is called the inverse square law. So the further you are away from that radiation, the less the dose is going to be. People seem to think that the dose is what is emitted, but it's not, it's what you're exposed to. And if you're a long way away from the source of radiation, your dose will be that much lower. Another thing that people tend to forget is actually we live on a radioactive planet, and you cannot avoid the radiation that we are subject to on the planet. So this is just a simple graph that shows you the amount of artificial sources versus the amount of natural sources. And you can see the natural sources are far more abundant. So about 80% of our dose comes from natural sources, radioactivity in the air, from radon, from the rocks that we live on top of, cosmic rays. If you're flying in an aircraft, you're going to get exposed to more cosmic rays because you're nearer the source of those cosmic rays. And there's also radioactivity, which comes from various isotopes that are present in food and drinking water. People get exercised more about the artificial sources as if artificial radiation is somehow different from natural radiation. It's not, of course, physically, it's the same. And about 20% of our dose probably comes from, our annual dose comes from medical sources. That varies from country to country, and in the States, your dose from medical sources will be higher than it is in Europe. We use radiation more sparingly, largely because it's expensive, and we have a different healthcare system from what you do. So we use a lot less radiation in investigative medicine and CT scans and things like that. But a very, very small amount only comes from the industrial sort of environment. But it's this bit, this 0.01% that people get really exercised about because they feel that that is somehow different and more dangerous than the rest of the radiation we're exposed to. So I'll talk briefly about the terms we use. These are very confusing. Now, becquerel is the measure of radioactive decay, not radiation dose. Becquerels have large numbers associated with them, and that tends to make people think that they're very high doses. That's not necessarily the case. The grey is the measure of the absorbed dose to a given tissue. That's the dose of 1 joule of energy absorbed per kilogram of matter. And if you're being correct about this, when you talk about a dose to an individual tissue, you should use the term grey. But actually, most of us now tend to use the term sievert, and that's a unit for measuring ionizing radiation effective dose. Now, it's the effective dose that is important in determining the health effect. This takes into account relative sensitivities of different tissues and enables us to sum the different types of radiation. So, for example, because a helium nucleus is quite large and has produce a large amount of energy if it comes into contact with cellular matter, it has a different weighting from something like a beta particle, for example. And then finally, what you hear a lot of if you look at the epidemiology literature is the excess relative risk. That's the percentage increase or decrease of the health risk in one group compared to a reference group. That's used not just for radiation, but for everything that has a health effect. So we use an awful lot of names for things, which doesn't make it easy when you come to talk to a non-expert audience. Here's a couple of fun things that you can do. If you look at the paper that's at the bottom of the slide, I recommend you do read that. That's actually a big review that was undertaken looking at the health effects of low-dose radiation. This table is taken from there, and this just gives you a range of different doses that you may be exposed to in your normal life. So, for example, a dental X-ray is a very, very low dose. A transatlantic flight is going to give you about 0.08 millisieverts because you're getting that dose from cosmic radiation. If you look at the UK average for total radiation dose, we're about 2.3. If we include medical diagnostics, it just goes up to 2.7. In the US, you're slightly higher. If you include the medical diagnostics, it can go up to about 6.2. Now, that's an average dose. Obviously, not everybody is going to get that. You can also get higher doses in areas of the world that have a higher radon background in the rocks. For example, in Cornwall, they tend to be very nice places because they're mountainous places. But Cornwall and Aberdeen and places like that in this country have a much higher background dose. It would be the same for Colorado in the States. If you want to have a bit of fun, go onto the University of Sydney website, and here you can plug in various things that you may or may not be exposed to in your general life. And work out what your radiation dose is going to be. I always give this to kids because it shows how bad smoking is, although it's actually not the radiation that gives you the cancer, it's all the other nasty things in smoking. But it's a really good way of teaching kids about radiation doses. Now, the most important thing is the magnitude of the health effect depends on the dose. The lower the dose, the smaller the health effect. So a dose to an individual depends on many things. It depends on physics. So it depends on the physical half-life of the element you're talking about. It also depends on the energy of the radiation that is emitted by that particular isotope. Then you have chemistry. Is this element taken up somewhere in your body and stored in a particular tissue? That's particularly important when we come on to talk about iodine, for example. It also will have an effect on how quickly that element is eliminated from your body, because your body is not stable. You are excreting all the time. You are taking food in and you are excreting it. So your body is constantly turning over. Don't think too long about that, because it tends to blow your mind a little. And then we have biology, and biology is probably one of the most important factors in this. We know that young people are more sensitive to the effects of radiation. Now, that may be one of two things. A, you've got longer to accrue in your life to get to the disease we might be looking at, but also many of the tissues in a young body are replicating. They're still growing because they need to reach adult size. And we think that is a key factor in the sensitivity of children to radiation. A high doses, we know that the health effect is directly related to the dose, and we call this deterministic. I'm not going to focus on that to any length, but I'll just clear that off in the next couple of slides. And at lower doses, the probability of a health effect is related to the dose. So you've got maths coming in there as well, because probability is a function of mathematics. And that is where it starts to get really difficult when you're trying to explain these effects. You're looking at a probability of something happen, not a definite thing happening. And then we call that a stochastic relationship. So let's quickly look at the high doses. Here's another table taken from that same paper. And here you can see that you have a very large dose. This is given in grays because it's talking about tissue, but equally it could be sieverts. If you have a very large dose of over about 5 sieverts to your whole body, about half of the population exposed to that would actually die because of effects on the stem cell system in the blood system that supports the rest of your body. You can get morbidity effects. Some of those are reversible. But the important thing is that here we're talking at very high doses. These are not the doses that we generally see to the population post a nuclear accident, for example. Now, this is something that took me a long while to get my head around, but it's really important. It's understanding what we mean by effective half-life and why different isotopes give us different effective half-lives, which is important when it comes to determining dose. So the physical half-life is the time for half of the radioactive isotope to decay. The biological half-life is the time for the body to excrete half of the radioactive isotope that we've ingested or inhaled. And the effective half-life is a combination of the both. So for long-lived isotopes, biological half-life is the equivalent of the effective half-life. And it's difficult to try and visualize that. So I want to imagine that you're in a shower and you've put shower gel on your arm, and the dose that we're going to talk about, the doses is how long, equivalent to how long it takes for your shower gel to disappear off your skin because it's been washed away by the water. So where you have an isotope where the biological half-life is much longer than the physical half-life, that's going to occur very quickly. It's a bit like being in a power shower. You get the dose very quickly within a power shower. It's the other way around if you have an isotope that has an extremely long physical half-life and a shorter biological half-life. It's a bit like standing under a dripping shower. To get the effect and therefore the dose, which is removal of all that shower gel, you're going to have to stand under a dripping shower a very long period of time. For alpha and beta emitters, they've got to be ingested or inhaled to have any effect. So that if they're going to do damage to the inside of your body, you have to take them in. Again, we live in a radioactive world. We are actually radioactive ourselves. And if you do that University of Sydney calculator, you can find out how much you're going to irradiate your partner as you're sleeping with them next to them tonight. Each of us receives about 0.3 millisieverts from isotopes within our bodies, and that includes things like potassium-40 and, surprisingly to most people, uranium and thorium. This is because many of the plants we eat, for example, bananas or Brazil nuts, have a high amount of potassium. They're good for you from that point of view, but because in nature a portion of the potassium is of an isotopic form, is the radioactive form, a proportion of the potassium in a banana will be radioactive. And obviously, if you're going to eat it, you're going to take it inside you. Now, most of these things have very long physical half-lives, and therefore the effective doses are very low, hence why we can eat lots of bananas and Brazil nuts without having any problems. For things like uranium, actually chemical toxicity is more of a concern than the radiation. And so the LD50, the lethal dose 50, is about 5 grams if you want to be stupid and eat uranium. And if you inhale, it's about 1 gram. But we actually excrete about 90% of it when we take it in over a day, over a period of a day. So you're actually not accruing much uranium in your body. And because it has this millions of years of physical half-life, the dose you're going to get is minuscule. So let's turn to the stochastic health effects, which are the ones that really exercise most people. This is where we have our information on what those stochastic health effects are likely to be. First of all, we have the large-scale lifespan studies that were set up after the atomic bombs in Hiroshima and Nagasaki. And here we have a very large population, or relatively large population, exposed to high-dose radiation close to an explosion site, far more than we get in a nuclear power reactor, for example, like Chernobyl or Fukushima. But we have low doses of the population further away because of that inverse square law I talked about earlier. And that was mainly gamma, but some was also alpha and beta. The Chernobyl accident is a little different in that we have a large dose of very small numbers of people, to the people who are actually on site dealing with the accident as it happened. And the dose to the majority of the population was very low, and you'll see what those doses are in a minute. And mainly beta from isotopes of iodine and cesium. We also have a series of cohort studies that have been in place for decades that are studying nuclear workers. And also we have some data on environmental exposure from areas of the world where there is a much higher background radiation level than in most of the rest of the world. So we have a lot of studies with large numbers of people in them. Now, again, going back to the paper that I suggested you read, this is a graph that is taken from that paper. I think really summarizes this quite well. So here you have all your large-scale studies. Now, we want large-scale studies because the humans are variable. And so in order to take account of that variation, you need large numbers of people to minimize that variation in your study. So here we have the Japanese lifespan study, which is the one in blue, which shows you those high doses that I was talking about that some of the population had. We also have a few clinical studies, ankylosing spondylitis patients, and some other accidents that occurred in the former USSR, Chernobyl workers, Mayak workers, and Tetra River residents. If you go and read the paper, you've got all the details there. So the important thing here is that people tend to think the Japanese lifespan study is the one that gives us the most information about all of this. But actually, if you look at this paper by Duplay, he has plotted every single person in that study in the area that they were in at the time of the accident, and you can see the doses that are there. So these points here in the blue box, the high doses, are actually restricted to very close to the explosion site. If you look in the center of this, you can see there's a lot of sort of gray dots, and that's because there were people who did not survive the initial blast. The blast and the heat damage was huge. If you're a military man, what you want to do is destroy things. So what you do is you get something that is going to obliterate people and everything in its path. So here we have actually very few people, relatively few people with high doses. And the majority of the people in this study, actually 84% of them, had the doses in the range that we're more interested in, so below 100 milligray. If we now look at that area on this particular graph, you can see that the area down the bottom, so this is 500 milligray, 100 milligray is there. You can see we have an awful lot of dots, some of which are above and some of which are below the axis. Now, that to me means actually we haven't got a clue what's going on there, because some of our studies are saying there is an effect and some of our studies are saying there is not effect. And even more important here, you've actually got the 95% confidence intervals, which give you some idea of the sample size at that point, but also the variability. So you can see that many of these doses actually cross this x-axis. If I can get my cursor to come back, there it is, cross this x-axis. Now, if I was to show you that graph and say to you, I've got a really effective drug, here's all my workings, you go, hang on, how do you know it's effective? Because down here, you've got above and below the axis. You don't really know what's going on. It's not very effective at all. But unfortunately, what we have done is to draw a line from the 0 point straight through all these points and say, that is our dose response curve. But actually, you can do anything you like down here, because I don't know where that dose response curve is. It linear? I don't know. Those points don't tell me that at all. So that's where we have a problem, because if you draw the line through the origin, it means to most people that no dose of radiation is safe. And I'm going to hopefully prove to you by the end of it that nothing is safe in life, but actually the risk from a low dose of radiation pales into insignificance when you talk about other risks in life. Okay, so another way of looking at that, which is somewhat easier than a graph. Scientists like graphs, but it's not always easy to see what they mean by it. So here's another way of looking at this. So if we take 100 millisieverts, which is the dose at which the epidemiologists will tell you we can definitely see an increase in cancer at that dose. So what happens if we give 100 Americans, and there are ladies here, but they're just wearing trousers, okay? So there are men and women on this picture. We've given 100 Americans, and we use Americans because you've got brilliant SEER database, which gives us loads of information about all the other things that affect our health. 100 Americans, 100 millisieverts, and we get one person who may get cancer as a result of that exposure. If you look at all the other causes of cancer, you're looking at about 42, and actually that's now probably heading up to 50, I'm afraid, in the States. Far more people are going to get cancer from other causes than from a dose as low as 100 millisieverts. We can't tell you exactly what is causing all of those cancers, and I can't tell you that is definitely a radiation cancer either. We have no biomarkers for it. So you can see at 100 millisieverts, we're actually looking at a very small effect in general health terms. And as somebody who's interested in not just radiation, but also cancer, I'm much more interested in what's causing the other 42 cancers on this slide. So there are really simple things that you can do if you want to avoid exposure. You can move away from the source because of that law I was speaking about earlier. You can avoid breathing in contaminated air or eating contaminated food. And if you remember what happened past Fukushima, the Japanese were really good at shutting down access to contaminated food. And they told people to stay inside, shut their windows and doors so they weren't breathing in the air. You can also wash off particles on the skin to avoid ingestion, because we all tend to suck bits of our anatomy whenever we feel like it. And so if you want to really avoid any ingestion on skin contamination, you want to wash the skin and get rid of it. You can also sometimes give stable versions of radioactive isotopes to block uptake, and that's often used as a way of mitigating the effects of iodine, radioactive iodine. However, you have to be careful when you give it, that you give it at the right time, otherwise you actually make the situation worse. And individual doses from nuclear accidents are much, much smaller than we think. And actually, a lot of what we do to minimize this may not always be necessary, but we err on the side of caution. So let's go through the 2 nuclear accidents that we've had more recently and see what we can learn from those. So 26th of April, 1986, this was the worst nuclear accident that has ever occurred in a power plant. It occurred during a test in one of the units, and a 4-unit nuclear power plant. The steam explosion blew the core apart and destroyed the building, and the accident occurred due to human error. Usually is a human that's involved in these things, and most importantly, poor reactor design. The design that was used at Chernobyl is not used anywhere outside the Soviet Union. It resulted in a large fire, the core was exposed, and radiation was released to the atmosphere. Let's cover off the deterministic health effects. So these are the health effects that occur at large doses of radiation, and only those people who were on site clearing up the mess immediately after the accident received these sort of doses. So there are 134 cases of acute radiation syndrome. 28 of those died. 3 people actually died as a result of the accident. One was a heart attack, one's buried under the rubble somewhere, and I can't remember what the third one was. So the total is 31, but 28 of those were due to radiation. In that cohort of 134, there's been 19 further deaths up to 2006, which is the last data we have. None were thought to be related to radiation. Quite a few of them were related to alcohol, smoking, etc. You know, things that we all do. Some of them were car accidents as well. If you've ever been to Russia, you will understand why that is not surprising. There's an increased incidence of cataracts in those with the highest doses, but that's, you know, that's something we can do something about. Many of us will have cataract operations as we get older. People say, well, what about, you know, what about, were they able to reproduce? Well, yes, 14 normal, healthy children were born to ARS survivors within 5 years of the accident. All of that information you can find in the UNSCEAR report. More recently, with the advent of whole genome sequencing, we've been able to look at triples of father, mother, and child, and look at the DNA from those people, and we can show that there's no transgenerational effects. So there's nothing that happens in the mother and the father that then is transferred to the children in terms of the genetics, which again is something that a lot of people worry about after the atomic bombs. Many people decided not to have children because they were worried that they would be prejudicing their outcome, that they might have a transfer some issue to them as a result of their own radiation exposure. That is not true. This is another aside for those of you seen the HBO series. This is the guy who was actually there, and you should go and read what he says about it, because it is not the same as the HBO series. Robert Gale actually smuggled in a new drug that was available in Switzerland, this thing called granulocyte macrophage colony stimulating factor, just GMCSF is what we call it, which he thought would support the bone marrow, which is the thing that gets destroyed by high doses of radiation and doesn't allow your blood to develop properly. This drug had been found to support that and enable your own system to recover after radiation exposure. We now use that extensively in cancer patients to support bone marrow recovery after chemo or radiation therapy. So although Chernobyl was a really nasty situation to go through, actually something good has really come out of that, which has a major effect on cancer patient survival nowadays. Interestingly, they also postulated it might be good for COVID-19. So it's clearly an interesting substance. And this is where you want to go to read his articles on this. He was there. He knows what happens, and he knows the real truth. So I'll just leave you to go and read those. But he also works in the States. I think he's at UCLA. He also works part-time in Imperial, where I used to work. Now, people think that the amount of release of iodine and cesium that we had from Chernobyl was actually the biggest release ever. Actually, we released an awful lot in the early 1960s as a result of above-ground atomic bomb testing, primarily in the US. But actually, some of that actually ended up on the UK soil because of the prevailing where the wind blows. And actually, we'd released far more iodine and cesium than we had from either Chernobyl or Fukushima. So this just puts the releases into some form of perspective for you. And remember, cesium has a half-life of about 30 years, whereas iodine is only about 8 days. So they're very different lengths of time they stay around in the atmosphere. So these are the doses to the general public, to those people not working at the plant, who were just happened to be living in the area when the Chernobyl accident happened. Those who were living closest in Pripyat, which is the village that served the power station, that's where people stayed when they were working at the power station, the thyroid doses are about 500 milligray, not evacuated, but resident in the contaminated areas. So these were a bit further away. They had doses of about 100 milligray. But there was a huge range of thyroid doses from less than 1 gray to 60 grays. So individual doses really matter when you're looking at the possible health effects, because it can be very variable. If you look at cesium-137, I should say that the iodine has all gone from the environment within 3 months because it has its short physical half-life. So after 3 months, the only thing that was really of a worry to the general public was cesium-137, which has a 30-year physical half-life. And the average dose to 5 million residents in the contaminated areas of Belarus, Ukraine, and Russia over a 20-year period from exposure to cesium was about 10 millisieverts. And the dose to those who were evacuated from the closest areas is about 30 millisieverts. To put that into some form of context, one CT scan is going to be, a whole body CT scan is going to be about 10 millisieverts. And you get that in a very short period of time. But we're talking about 20 years to accrue that sort of dose. Now, that's really surprising, but it tells me why we don't see any effects of the cesium in the environment. The iodine is a different matter. So the consequences to the population was that we first saw a report of an increase in thyroid cancer in 1990, particularly in children. And in the West, we didn't believe it. I mean, this was the Soviet Union. We didn't believe anything they said. You know, they were trying to get money from us. There were loads and loads of excuses why this possibly would not be right. But they did allow a few of very eminent pathologists and endocrinologists to go out to look at the children, to look at some of the samples that they got from those children and to say, yes, this is a genuine increase. But every cancer has a spontaneous incident. No matter what cancer you're talking about, there is a spontaneous incident. But in thyroid cancer in children, it's usually vanishingly low, ranging about 0.5 to 1.5 per million per year. And what we saw in 1990 and going forward was in those who were exposed as children, we saw a massive increase, about 100-fold. So there was no hiding this. This was such an unusual thing to see in the population, to suddenly see a lot of it. Everybody went, okay, well, what's causing this? And the answer, of course, it was the radioiodine, the iodine 131. Basically, the iodine takes up and stores iodine because thyroid hormones contain iodine. Your thyroid hormones control your metabolism. Without thyroid hormones, you're really in trouble. Some areas around the Chernobyl area were moderately iodine deficient, and that might have increased dose. And the way to sort of think about this, if you have a dry sponge and you put it in a bucket of water, it's going to take up a lot of the water from the bucket. If you have a wet sponge and put it in the bucket of water, it's going to take up much less. So having less iodine in your diet, being moderately iodine deficient, means you're going to take up more radioactive iodine when it becomes available. As I said before, the entry and storage of radioiodine can be blocked by the gland with stable iodine, but you've got to give it at the right time, and you've got to give it before the radioiodine comes out of the reactor. That's difficult to do if you've got no containment, and there was no containment around Chernobyl. So if you give it too late, basically what happens is you trap the radioactive iodine within the thyroid, and it can't get out, and therefore it's going to release its radiation while it's in the thyroid. So why in particular children? Well, we know we use radioiodine to treat thyroid cancer, ironically, and we know that adults don't seem to have the same effect when exposed to radioiodine. So why is this? Well, it's partly exposure. Children tend to drink more milk, they eat more dairy produce than an adult does. But they also have a small thyroid, which gives it a larger dose to the gland just because of the physics of the release of the radiation. Most importantly, it's because the thyroid is still developing. So the thyroid needs to grow to maintain the hormones to run the body's metabolism. So losing cells when they're mutated is not an option. You still need those cells to produce the thyroid hormones. So what you will get is an increase in the mutated clone size as a result of development growth. So one cell is mutated by exposure to the radiation, but instead of the body going, oh, there's something wrong with that cell, I can get rid of it, that cell tends to stay around in a developing organ. And so you get a patch that has the same mutation, which then increases your chances of getting further mutations and therefore developing cancer. So this is your normal pattern. This is the UK, but the US is very similar. Here is your normal pattern of thyroid cancer, very rare in young children, increasing as you get older. This is what we actually saw in Belarus post the Chernobyl accident. And here you can see that over a period of time, we have a cohort of people, starts in young children, then we see the increase in older children, adolescents, then we see the increase in young adults. So here we have a cohort that is carrying a risk from being exposed to radiation with them as they age. Now, the reason that that curve in children falls off very rapidly is once you were not exposed to radioiodine in the environment, so you were born 6 months after the accident, there's no radioiodine remaining in the environment, and your thyroid is not concentrating it while you're in utero, you then find that that frequency goes back to where it was before exposure. So those who were born after 1st of January 1987 have no risk of thyroid cancer from exposure to the radiation. Okay. Now, the good news about thyroid cancer is you can treat it very easily. You take the whole of the thyroid out, We give radioiodine treatment, high doses of radioiodine for any bits of treatment, high doses of radioiodine for any bits of cells that we've missed for metastatic tumor deposits. And we can then replace the hormones by giving very cheap, actually, hormone replacement. I think it's about a penny a pill for a thyroxine, for example. However, there is a recurrence rate. So about 30% of those people their tumor will come back. Most of those you can treat either by simply removing the lump and following up with radioiodine. The recurrence rate leading to death is very, very low. In England and Wales, with a 20-year follow-up in children who had thyroid cancer, the death rate was about 3%. The studies that have been done post-Chernobyl thyroid cancer, and there's one there by Mike Tuttle, who's at MSKCC, suggests about 1%. We are getting better at treating cancers, all cancers, including thyroid cancer. So actually, we would expect that death rate to fall anyway, because we're treating better with time. And the England and Wales one, obviously 20-year follow-up, we're looking at people operated in the 1960s. So these were the radiation health consequences of exposure from Chernobyl. There are those 28 deaths from acute radiation syndrome, 15 deaths we know of from thyroid cancer in the 25 years that were after that. We haven't had any reports since. And of course, now with the Ukraine-Russia war, everything is all over the place. So we can only deal with the data that we've got at the moment. It has been predicted that there would be 16,000 excess thyroid cancers in total. Whether we're going to reach that, I don't know. At the moment, we're around about 5,000, we think. There's about a 1% mortality rate. So that should work out, even in the worst case scenario, 16,000 of 160 deaths attributed to radiation over a period of about 50 years. Thyroid cancer does not kill you quickly. We don't have any increase of thyroid cancer outside Belarus, Ukraine, and Russia. We have no evidence of effect on fertility, malformations, and infant mortality. We wouldn't expect to see that at the doses that we're talking about. However, some people did have abortions because they were scared. And that, I think, is one of the things that is the worst consequence of fear of radiation. You prevented a human being born because you're scared of something that's not going to hurt you. We can't have any real conclusions on adverse pregnancy outcomes or stillbirths, simply because when this happened, this was all part of the Soviet Union. They were very secretive. So those studies just could not be done independently. But at the doses we're talking about, highly unlikely. Heritable effects not seen. You've seen the study I referred to before. That was from the people who were called liquidators, so the people clearing up the mess of the accident. They had much higher doses than the local population. We didn't see anything in their blood samples. We're not likely to see it in anything else. And interestingly, we have a lot of epidemiological cohorts that are looking at those liquidators, so those who had higher doses than the general background population. And we still have yet to see any conclusive evidence of increase in other cancers. There was one possible increase in a type of leukemia that was not normally associated with radiation. That was in one of the various studies, not in all, and really the jury's out about that. So you will see people say there are going to be 4,000 deaths as a result of the Chernobyl accident. Those come from those studies. They're not deaths, they're cases of cancer. You don't necessarily die of cancer these days, so you have to be careful how you use the words. And actually, we don't have any evidence that there is an increase in those cohorts. So the only health consequence from the physical exposure to radiation from Chernobyl has been thyroid cancer in children, those who were children at exposure. And that's been due to high thyroid doses above about 100 millisieverts in many of them. There are no biomarkers that we can see that enable us to go, yep, that's a thyroid cancer caused by radiation. So unfortunately, we can never separate how many of those are spontaneous cancers and how many are actually due to radiation. We still have no marker to be able to do that. But the most important thing, and I think the take-home message from this, and the message we did not get across before Fukushima happened, was the most damaging health effect has been psychological stress and the fear of radiation. Now, that's something we can do something about. If we can disband that fear, then that population is not going to be subject to those health pressures. So let's quickly now look at Fukushima. Well, the mean doses to thyroid are about 100-fold less than the Chernobyl evacuees. So already you have much lower doses to contend with. Those who were evacuated, and they were evacuated not just because of the radiation, there'd also been a large tsunami and a huge earthquake, which had completely wrecked all the infrastructure there. but 93% of those had estimated doses of less than 2 millisieverts in the first 4 months post the accident. You know, that's less than an annual dose of radiation in the UK, for example. Whole body time points at later time points showed that nobody had any detectable levels of cesium-137, partly because the Japanese had broken the food chain and were making sure that they didn't eat any contaminated food. We are expecting to see absolutely no discernible health effects expected from the radiation at those doses, but there were 2,000 deaths as a result of the evacuation. And if you compare that with about 20,000 from the tsunami, although all we hear about in Fukushima is the nuclear accident, actually, there are no deaths from that. The deaths were as a result of our reaction to it. And it's important that we learn that evacuation not done in the right way, and some of this was panicked evacuation because they just wanted to get people out there. They didn't have medical support for people who were ill or for elderly people, and some of them actually died on the boat, on the buses that were taking it from their old people's homes. So we really need to learn those lessons and make sure we don't repeat that in the event of another accident, which is unlikely, but you need to learn lessons from things like this. So what did the Japanese do? Well, they thought the best way on this is to study people's health. So they initiated a large population-based health survey in 2011. A lot of us in the West were slightly more nervous about this and the way they were going about it, because we didn't think it was actually going to address people's fears. And part of the reason for that is it's very difficult to separate radiation consequences from health consequences of societal disruption. So you've just evacuated a whole load of people, shoved them in places where they have no family support. Of course, their health is going to be different. And you're trying to tease out what the effect of radiation is. So you need to be very careful when you conduct these studies that you do the right controls, for example. Because of the fact there had been an increase in thyroid cancer after Chernobyl, the Japanese thought that the best thing to do was have a large-scale ultrasound screening of the thyroid of the population aged under 19, which is the age at which we knew were more susceptible to getting radiation-induced thyroid cancer after Chernobyl. So they thought this would be a really good idea. But unfortunately, large-scale ultrasound screening of any sort, it doesn't matter whether it's thyroid or for any cancer, will uncover things that are there in the population anyway. And if you don't have the right controls and the right messaging around that, it can really worry the population. So you saw headlines like this, and it's just not true. And there's a good reason for this. So the old way of detecting a thyroid nodule, and that thyroid nodules are frequently found, not all of them are cancers, is to stand behind the patient and put your fingers around the patient's neck and feel for a lump. Now, that's not very sensitive, obviously. And by doing that, you will find that 2 to 6% of the population have actually a thyroid lump, not necessarily a cancer, but have a thyroid lump. You then have to investigate those people further. If you use ultrasound, it depends on how sensitive your ultrasound is. And of course, the Japanese, being the Japanese, had the best ultrasound they could possibly find. If you use ultrasound on that same population, you'll discover thyroid lumps somewhere between 20 and 35% of the population. If you do the ultimate study, which is to take out a thyroid from somebody who has died and carefully section it and look for cancer in that gland, it can range between 8 and 65%. So when you get to an elderly population, probably about half of the population have a very tiny thyroid cancer in their gland, which is going to do absolutely nothing. We don't do the studies because it's extremely difficult and very expensive to do. But if we actually took hundreds and thousands of people and carefully sectioned every single tissue as people got older and died, we would find that we're riddled with cancer, basically. We're riddled with small tumours that are not clinically apparent and are not going to do anything that's going to ultimately kill us. We see an increase, for example, in renal cancer. Now we're scanning people's kidneys. We are finding more renal cancer, particularly in an old population. What happens when you screen the thyroid is here is your normal population distribution. So this isn't a population that has not been exposed to radiation, but this is the normal frequency that you would expect to see, judging by non-screened approaches. And again, you see that same curve, very rare in young children, but increasing as you get older for both males and females. It peaks more in females. We don't know why, but females tend to be more susceptible to thyroid cancer than men. If you screen that population, all you simply do is move that curve to the left. So now you start seeing thyroid cancer in younger people. It doesn't mean that that's caused by radiation or anything else. It's simply caused by what we call clinical ascertainment. You're finding it because you're looking for it. And you're just actually shifting the diagnosis by a few years. That's why we screen for other cancers. We want to find them earlier. But with thyroid cancer, that's actually counterproductive, because by finding them earlier, it's one of those cancers that actually we don't have that much information that would show us that it really is that much better to operate and take the thyroid out, because of all the other things that come into play, like replacing thyroid hormones, being monitored for the rest of your life, especially if you're a woman, needing to be careful going through pregnancy, etc., when obviously the body is going under an awful lot more stress and needs more careful monitoring. And also for a young person having an operation on the neck, you've got nerves in the neck that control speech, etc. So you have to be really careful before you start operating in young people for a disease that is not going to do anything to them necessarily. You will need watchful waiting, but you don't need to panic about it. So screening actually didn't help at all. We just uncovered what was already there. So the radiation has not caused any thyroid cancer in the population. That increase is simply due to clinical ascertainment. Now, let's quickly go and look at water, because this is the thing that's been in the news most recently. What the Japanese did was use a very complicated technique whereby they removed all of the elements they could possibly remove using this ALPS purification system, and they were left with tritium, which is a form of hydrogen in water. Basically, the plant is an area where water ingresses, and also they have to keep the plant cool by pumping in water. That water picks up radioactive isotopes, needs to be cleaned before you can then do anything with it. So the Japanese have been typically Japanese, have done the best they can at this. They've removed everything else apart from very trace elements of some of the radioisotopes and tritium, which you can't remove. And they stored it all in large tanks, which you can see there in the blue, next to the reactor site, thinking we'll have to release it eventually, but if we keep it long enough, because tritium has a half-life of, I think it's 14 years, then if you keep it long enough, within 14 years, you've actually got half as much as when you started out. So it's a good thing to do, but eventually you're going to have to take a decision what you're going to do with it. And so they've now agreed that they will release it to the Pacific Ocean. That caused consternation because people were worried about it getting into the marine environments. But actually all the studies show that doing that was entirely the right thing. And you probably could have released it a lot earlier than the Japanese did. The reasons are that tritium emits a very low beta radiation. It's a bit like your DNA being wafted by a feather. Sorry, its physical half-life is 12.33 years, not 14. But its biological half-life is 10 to 40 days. So therefore, the doses of the tissue is going to be very low. We know bioaccumulation does not occur because all of aquatic creatures are like us. They take in water and they get rid of water. So there's constant turnover. So there's no accumulation. They've done very careful modeling, and the potential radiation doses are ridiculously low. And they've also carried that into, what humans eating fish that were in the Pacific Ocean near the reactor, what would be the potential doses from those. So there's no human health effects nor effects on the aquatic environment from radiation exposure from release of the Fukushima water. But there are effects on the well-being from fears over radiation. Again, that fear, not the radiation itself causing problems, resulting in effects on people's livelihoods, particularly the fishermen. I think we've all got a role to play in mitigating this unfounded fear. If you want to go and read more about this, read this paper by Jim Smith. He's my sort of equivalent on the environmental side. He works in the University of Portsmouth. And he has really nicely put this into some context, showing you how much tritium is normally released by other things. And a lot of the countries around Japan have been up and down and moaning that the Japanese are polluting their water. Actually, Korea releases more, so does China. The UK is not without blame either. But if you look at the amount of natural tritium from the natural processes in the environment, all of that is sort of pales into insignificance So, you know, really and truly, we're not actually adding much to the ocean. Nuclear waste. Now, the radioactive elements of concern here are the actinides. These are the long-lived isotopes, like uranium and things like that. They're heavy, they're non-volatile, so we don't have to worry about them getting into the atmosphere, but we do have to worry about where we're going to store them. They're mainly alpha emitters. Alpha is relatively easy to stop. You can put a piece of paper and that will stop an alpha emitter. Some have very, very long half-lives. So they're going to be present in the environment for a long while. So that gives us a headache in terms of intergenerational ethics, etc. And the concern is actually leaching into aquifers. So will this stuff get carried in underground water into the water that we're then subsequently going to drink? But as I said before, with all of these, the chemical toxicity is more of a concern than radiological toxicity. You'd have to be exposed to a hell of a lot to even see the chemical toxicity. The reason we are happy about the way we've chosen to store this material long term is simply that the Earth's actually done it all before. And this is a really good thing to go and look at. The Earth actually had its own nuclear reactor that went on for about 100,000 years. And so we know that if this stuff gets put back underground, it's not going to go very far, because we can look at this area in Gabon and see where those isotopes have actually moved to, even when there was a water flow coming through. And incidentally, if you go swimming in the sea, you're actually exposed to quite a lot of uranium in the sea. So, you know, you can't avoid uranium and these actinides. They are all present. And obviously, anything that decays from uranium is also present. So, you know, we are exposed to them all the time. We have them in our own bodies. And really and truly, we are worrying probably about something that doesn't need to be worried about at the doses we're looking at. So the chosen way of dealing with radioactive waste is, from the point of view of future generations, we want to make sure this is safe, that nobody can accidentally come across it. We want to protect it so that it can't leach out into aquifers. So we pack it into specialized containers, which we then bury about a mile underground. When I asked somebody in the government in the UK, why did you choose a mile? I understand it's because in the next glacial age, we might lose about a mile of topsoil. That's the reason why we bury it a mile underground. I don't really think we'd actually be worried about being exposed to nuclear waste in canisters, etc., if there's a large ice age threatening us somehow. But it will be stored, and there are two, I think, one in Sweden and one in Finland. I can't remember which one is now operating, but certainly both of those countries are building these geological disposal facilities. We're still arguing about it in the UK as to where it should be. We've been arguing about for the last 15 years, but that's what we do in the UK. We spend a lot of time talking until we finally do something about it. The Swedes have done a lot of modelling again about this, and they've said if we use this engineering, and assuming we got it wrong and all these casks leak, and put it in underground like this, those living directly above the storage site would only be exposed to about 0.014 millisieverts per year. Okay, that's equivalent to flying for an airplane in 3 hours. 1% of the average dose a person globally gets from naturally occurring radiation, and less than 0.5% of the average dose we get from all sources per year, considerably less than that in the States. Okay. So why are we worrying about this? Let's try and put this into some form of perspective, because all risks are relative, and we need to be able to take account of other risks and say, is this as bad as something else I do in my life? We do this naturally. We don't think about it most of the time, but let's have a look at this. So again, taken from that paper I've been calling on, this is an atomic bomb survivor who was within that blue circle, so exposed to the largest amount of radiation and survived. They would lose about 2.6 years of their life. If you've got an old white, 35-year-old white, severely obese male, obesity is much worse for you than being in that circle. And if you're a smoker, it's worse again. And if you look at the number of attributable deaths worldwide, radon, we think, probably results in about 99,000 cases of lung cancer, but air pollution and tobacco smoking are so much worse. If you looked at the average life of loss of life expectancy for all of the members in that Japanese cohort who received any dose at all, it's estimated to be about 4 months. So anybody with any radiation over an 80, 90 year, because the Japanese live a long while, period, would be likely to maybe lose 4 months. And that would be largely those in the highest doses, obviously. Put it into more context, here's just a series of things from the US. And you can see that, you know, smoking, we know, is bad for you. Going out and not using a sunscreen is also bad for you. Driving in a bad way is bad to you. And actually quite a few people, 454 out of bed and die in the US. Not quite sure why they've fallen out of bed. Maybe they've had a heart attack, but 450 evidently. And if we put that into context with the number of deaths from radiation over 50 years from Chernobyl, so that's taking into account those who died from acute radiation syndrome, those who might die from their thyroid cancer, and adding a few on in those cohorts that we don't know whether they're going to get cancer or not. It could be anywhere between, say, 200 to 2,200 over a 50-year period. And you look at the figures above for other things that we do, you begin to wonder, why are we so worried about radiation? I'm just going to finish on a quote by a hero of mine. He's now retired, but David Spiegelhalter was professor for public understanding of risk at the University of Cambridge. And he is out to quote on things for a lot of things in the media, a lot of health-related things. This was to do with alcohol consumption. But I think the bit at the bottom is the most important. Given the pleasure presumably associated with moderate drinking, no safe level does not seem to be an argument for abstention. There's no safe limit for driving, but the government don't recommend that you don't drive. And come to think of it, there's actually no safe level of living, but nobody would recommend abstention, i.e. you don't live at all. I think we have to get used to the fact that radiation at low doses is not as dangerous as we think. Unfortunately, it's been overhyped by certain groups in the population for their own reasons. And I think, unfortunately, as scientists, we're always on the back foot trying to put that evidence in front of people. Now we have 30, 50, 60, 70 years of studies of these various exposures. If you want more information, although it's an industrial site, the World Nuclear Association has some really good web pages on Fukushima and Chernobyl, and there are a variety of other things. And I would go and read the statement of the national evidence base that was written by the Oxford Martin School, which is the paper that you've seen me referring to. That's written with an idea of general public understanding. You can tell us whether we got it right at the end of that. Okay, that's all. Thank you very much. Let me stop sharing so I can see you again. There we go.
All right. Thank you so much, Dr. Thomas, for sharing this educational information with us. And thank you everyone else who's joining us today in the middle of the day here in the US. Remember to put your questions in the chat if you have any. Just some quick information here. If you want a certificate of attendance, you can go ahead and email Salemi Hernandez. She put her email in the chat. And also this recording will be posted soon to the Southeast CCL YouTube channel. A couple of questions that were in the chat earlier. From Nadine in New Jersey, she asked to avoid breathing in contaminated air. Does like an N95 or equivalent mask help at all?
I can't answer that. I'm not an expert on that. But the general advice would be, as if it was a chemical exposure, and there's no reason that we treat radiation differently apart from our own mental issues. You just stay inside with the doors and windows closed. And the other bit of information the Japanese gave to their population, which unless you've been to Japan, you wouldn't necessarily understand, don't put your washing outside. People in Japan dry their washing on their balconies. And so obviously if you've put your washing outside and a radioactive plume comes over, you've got a chance of bringing contamination into the house. So I wouldn't bother about masks. I would stay indoors, keep your doors and windows shut.
All right, thank you very much. Also, Paul from California had a question about dosing. He said, how important is the total dose versus the dose rate?
That's a problem. We still don't know the answer to that. A lot of people argue that there is no difference. I think there has to be, simply because if you give radiotherapy, and remember, radiation is a really effective treatment for cancer. If we didn't have radiotherapy, an awful lot of people would die of cancer. But we actually give very, very large doses. Admittedly, it's very focused, but it's very large doses. There is a degree of scatter when you do that, but we fractionate it. So we give people a dose and we give them time to recover. So I have a suspicion, although we cannot prove it with any of the studies we've done, and we probably never will be able to do the studies to prove it because we can't do that sort of thing to a human population, then I suspect if it's fractionated, you're giving the body chance to recover.
Okay, thank you. Salome, did you see any other questions in the chat?
Yes. By the way, you can raise your electronic hand too if you want to ask a question as well. There's one from James. Has any correlation between natural background radiation dose and cancer incident being observed by any studies?
Nope. No. I mean, that's one of the things. If you, again, go and read that restatement by the Oxford Martin Group, that will give you all the information that we have about the studies that have been done there. And there are areas of the world which have much, much higher background rates. For example, Ramsar in Iran, you know, areas of Brazil. People actually sit in thorium sands in Brazil because they think it does you good. And I've seen in Japan one spa that said we have injected extra radon into the air. Which of course is, you know, it's a radioactive isotope. We've injected radon into the air because we know, you know, it's good for you. So radioactive spas, people sit in all the time. You know, there is just nothing there to show that the levels that people experience in the natural environment show an increase. Radon is possibly the only one where there's a query, because we think high levels of radon in air, which is trapped within houses, may give you a tendency to get lung cancer. And that's why many areas of the world where they have natural background, high levels of radon actually have preventative measures in place. But then again, you look at those figures for radon and you compare them with particulates, and you can see that actually, you know, running diesel cars, running any form of cars that uses oil-based material is probably an awful lot worse for you.
All right, Niels, you had a question?
Yeah. So first, thank you for the lecture, and second, you talked a lot about cancer risk in relation to radiation exposure. One could also imagine other health effects, cardiovascular effect,
again.
or neurological effects. Were there any studies and any
there have been lots of studies. There have been lots of studies, but we just can't see anything that really stands out. Again, if you read that article, it will give you all of that information. And behind that article, there's lots of annexes that will point you to the original studies. It took about 6 years to write that because we had to go through all of these studies very, very carefully. But it's really difficult to know at the doses we're talking about, not very high doses, but the doses we're talking about, whether there actually is any cardiovascular effect. We think there is an effect maybe on cataracts at around 50 millisieverts, but we're all exposed to radiation that's going to give us cataracts anyway. So, you know, even 50 millisieverts, and that's a lot higher than the doses from Chernobyl in the general population. You know, it's really difficult to find anything because everybody's so variable and the effect is so small. And there are other things that give you that same effect. For example, a bad diet will give you a larger cardiovascular risk, for example.
Understood. Thank you. Maybe one last follow-up question. At the radiation levels where increased cancer rate has been found, has there at those like higher elevated rates been any indication of other health effects? Or,
well, I mean, no. Again, if you read that you'll find all the information is there. The only thing that we can say from a nuclear power plant accident is radioiodine, and make sure children are protected from that. That would be our only advice. But actually, the doses that you have to see anything tend to be an awful lot higher than than the interventional levels that we would set at any intervention at. So actually, the best advice was the advice the Japanese gave: stay indoors. Don't eat contaminated foods. So don't eat leafy greens you've grown in your back garden. Don't drink milk that's come from a backyard cow. Which, of course, in the Chernobyl area, they couldn't do that because that's all they had. But in Japan, in a highly organized society where you can bus in milk and water and things like that to people, Because the interesting thing that we did find in Chernobyl, it was not actually breathing it in that was the problem. The major dose came from consumption of contaminated material. So milk from the backyard cow, or vegetables that you've grown in your own allotment, where you'd had iodine that had come down in the rain, settled, and people had just eaten what had come out of the ground.
Understood. Thank you.
Thank you.
There's a couple of questions in here in regards to like mining or living near other things. I know you covered that a little bit, but is there anything else you want to add to where people are living?
Well, if you go and look at the University of Sydney's sort of dose calculator, you'll find that living near a power plant, there's a nuclear power plant, you get less radiation than if you live near a coal power plant, where you're actually burning fossil fuels and releasing the radioactivity that's present in the carbon-containing material that you're burning. So counterintuitively, you know, we are exposed to this all the time when we're using fossil fuels and things like that. Even fracking will release a small amount of radiation. Nothing to be worried about, but we think that, you know, if it's natural and not to do with the nuclear industry, it's perfectly okay. The answer is yes, it is okay, but we should be putting that into some form of context.
Thank you. James, you had a question?
Yeah, you mentioned the 2,000 deaths at Fukushima from the panicked evacuation. And I'm wondering if you had any thoughts about, you know, maybe changes in policy, you know, like relying on shelter in place more. And then follow-up question is, then there's the long-term relocation of the population. You know, I personally think that that's an example of unjustified overreactions having a large impact on people's lives, more so than the radiation itself. So that follow-up question is, do you think they should have relocated them out of the area for that long a period of time?
The problem that you have in Fukushima, and I've been out there many times, is it wasn't just the radiation. What they did was they closed the area where the radiation was higher, so they didn't put the infrastructure back in. So there was no gas, there was no electricity, you know, because not because of the radiation, but because of the tsunami and the earthquake. So to make it safe in Japanese terms for the workers to go in to, you know, make everything okay again, they decided to evacuate people for longer periods of time. If it hadn't been a triple disaster and it had just been the nuclear disaster, I would have said, no, don't evacuate people, get them to shelter in place. This is really difficult getting politicians to do this, mind, because the knee-jerk reaction is get them out of there. But we've had, you know, I've seen scenarios where if you think in an area of rural England, for example, where you might have a folk festival or something going on, and one of our French plants has a problem, that comes across the channel. You are putting people at risk if you suddenly say to them, right, everybody get in your cars and leave, because you're going to have more accidents on the road, you're going to have more stress. Whereas actually, if you said stay indoors with your doors and windows shut and shelter in place until the radioactive plume has gone over, and remember, this stuff is carried in the atmosphere in the wind, so when the wind has taken it out of the way, it's perfectly okay to come out again. You're just not going to get the levels of contamination that people think you're going to see, unless we have another Chernobyl, and we're not going to have another Chernobyl because all of our plants are engineered very differently from Chernobyl.
It strikes me as a communication issue. You know, you said the reality is that they weren't being allowed back because of the earthquake and tsunami damage, basically. But the way, even I didn't know this. I thought they were not allowed back in because of radiation. And
well, that's what we were told.
Yeah.
But actually, when you've been out there, you couldn't have moved back anyway and lived there because the infrastructure wasn't in place.
So that's
yeah. I mean, you know, you need decent sewerage, you need utilities, etc. if you want to be able to live a reasonable Western style of life. And if you haven't got that, you know, you're not going to allow general population movement back. But that's part of the reason that was a unique situation. And we tend to only think about the radiation. But actually, I was there 6 months afterwards and absolutely shocked about how far huge great boats had come in on that tsunami. It's something that we find really difficult to comprehend. They evacuated huge numbers of people when that tsunami was coming in, something we would not be able to do in the US, certainly wouldn't be able to do in the UK because nobody would listen to anybody. But the Japanese know what to do, and they pulled a large number of people out of that area where the tsunami hit, which wasn't exactly the same place as where the radiation hit. That was the problem. So it's really difficult to unpick that situation. But the worst thing for me was knowing that people were moved. And I actually stood at one of the old people's homes that overlooked the plant. It was a concrete building. Several people from that place had no medical help because the doctors had run away. No medical help. They didn't have enough water and food to be evacuated, which was going to take a long while because of the state of the roads. And so people died because of the knee-jerk reaction of let's get them away, rather than saying, and there's a good paper by a guy called Hasegawa in the Journal of Clinical Oncology, where they looked at those who were evacuated as a knee-jerk, get them out of there quickly, and those who were evacuated with the appropriate medical support. Those who were evacuated with appropriate medical support were absolutely fine. Those who were evacuated as a knee-jerk response were the ones who had problems. And many of them have actually had psychological issues and psychological stresses because of that forced evacuation, knowing they were never going to see people they'd grown up with, go back to their old ancestral sort of lands. There's an awful lot of emotion in Japan in where you're from. And so, you know, it's caused an awful lot of problems, all of which I think could have been avoidable because the risk to health from the radiation doses was minuscule.
Thank you. We're kind of focused a little bit on the energy side of things. And Matthew, I think you have a related question.
Thanks. Yeah, actually, someone answered that question in the chat, but I did have a question about the storage of waste. This has been really useful, especially to someone like myself who's not very well informed. Thank you. One of the things that I sometimes hear from people as an objection to using nuclear power is that to safely deal with waste, we need to be able to store it for a very long time, and that's not feasible for human societies to pull off. I wonder if you have any comments about that.
Well, actually, because of the rate of decay of these things, it probably only needs to be stored with a degree of security we're looking at for about 100 years, because the rate of drop-off is extremely quick with the half-lives that we're talking about. You're then down to sort of low-level release of radiation, which is perfectly okay. I mean, what we're exposed to all the time in the world. So people worry about that. My concern is actually, we talk about waste about nuclear and we ignore it for things like solar panels. Solar panels, cadmium and other heavy metals, those are extremely toxic and don't decay in the environment. What are we going to do with all the waste from that? You know, we tend to find things, we've got over the Chernobyl and Fukushima and deaths from accidents, and now we're focusing on the waste is too dangerous. Well, we keep finding excuses for not actually using something that could probably help our climate an awful lot, and ignoring other waste streams that are coming on because we're using, I mean, we use vast numbers of solar panels in this country, which is a miracle because it never sun shines here, and loads of wind turbines. And a lot of that involves heavy metal waste. That's got to go somewhere. And that's not going to decay in the environment either. So we focus on nuclear waste, but we forget about waste streams from other things as well. But to me, you know, the Earth has proved if you have a nuclear reactor and you leave it in the ground, it stays where it is. So all you've got to do is to make that area secure. And who knows, we're digging up waste dumps now to get things out that might be useful. We may have found a better way of recycling that in the future. So actually, do we want to lock it away and deny? I mean, there's an awful lot of ethics around this. We think we are being good by protecting our future generations by locking it away, but actually there's stuff that could be useful for that generation to use in various things, including heat generation. So by locking it away, actually, are we preventing those generations? It's extremely difficult ethical situation to be in. But in terms of, am I scared of nuclear waste? No, I'm not. I've been in Sellafield. I've stood next to casks that contain radioactive waste, and there's just no dose coming off of them at all because they're all in concrete, so nothing comes out. You know, why are we so worried about it? We know what to do and we can store it effectively.
Thank you so much. It's all in perspective. Gabrielle, you have a question?
You talking to me?
I'm talking.
Yes, go
Okay.
ahead.
All
Your
right.
hands up.
Yeah. Okay. Hang on. Okay. Yeah. What about the mining process. I mean, how bad is it for the health of mine workers?
Again, you know what the hazard is, so you can put in risk mitigation, and it's no more hazardous than any other form of mining. And don't forget, you've got to mine cadmium and lithium as well for the things that you're going to put in your solar panels. None of this comes without any risk, but uranium is not, the most dangerous thing. I know people tend to think it is, but it's not the most dangerous thing. As somebody who's a toxicologist and pharmacologist by training, heavy metals terrify me because they're neurotoxins. And they don't go away. Radiation is something that I can live with and I can understand.
Okay, how about the nuclear, the workers who handle the nuclear waste?
They're protected. They're not just doing their nothing. Everything gets monitored. You can't do anything without being monitored if you're a nuclear worker. So you'll know exactly what your doses are. And then most of the doses, I think the average dose is below 1 millisievert for nuclear workers in the UK. I don't know what it is in the US. 1 millisievert per year. That's half of my annual dose.
Yeah, which is like nothing much.
Exactly. It is nothing much. Flying to go on holiday will give you more of a dose.
Okay, well, thank you.
Ryan, you have a question?
Thank you, Dr. Thomas. This may be an insensitive question, but I pose it to a lot of radiation safety professionals.
Mm-hmm.
How could a member of the public hurt themselves with radiation? Is it even possible to?
It's possible to do it with an unshielded source. So there was an occasion in Guiana in Brazil where a hospital was being dismantled, and somebody took what they thought might be a quite nice, pretty ornament, which was actually the radioactive source for a radiation machine that you used to treat cancer with, and put it on their mantle shelf. Somebody else also broke another one up and scattered the bits around. So if you have an unshielded source like that, which is giving out a lot of radiation, yes, it is possible to get hurt. If you treat it with respect, then it's fine. But I would put another one to you. If you have a headache, you'll take 1 tablet of acetaminophen, paracetamol, but you wouldn't take a whole box. You don't take a whole box because it will kill you. And it's a really nasty way to go. So we understand the concept of having respect for things and treating them properly. If we just did that with radiation, I don't think we'd have a problem.
Yes, I feel like some people think radiation is out there in the wild, that they can come across it.
It is. You're exposed to it now. I'm exposed to it. I'm drinking water. There's radiation in my water. You cannot avoid it. You're breathing it in. When you swim in the sea, you're exposed to uranium. You cannot avoid radioactive substances if you want to live on this earth. It's that simple. And just because those radioactive substances have been used in some industrial preparation doesn't make them any different from the ones that are there. It's the laws of physics. They're the same things. They are exactly the same things. But it's just we have a concept that anything that man has invented, and we see it with the pharmaceutical industry as well, anything man has invented must be more toxic than something in nature. But most of our drugs actually came from nature, from the early studies that we've done on subjects called pharmacognosy. And many of the worst toxins that we have, we find in nature, like snake venom and things like that.
Interesting.
But it's this concept that we have. If we've done it as man, it's more dangerous than nature. Actually, nature's pretty violent and pretty nasty.
Thank you.
Zero, who's another a leader in our nuclear action team, I'm wondering if you have any questions or anything that you want to add first?
No, thank you so much for taking this time. And we have to be mindful. So Dr. Thomas, I know this is beyond your hour, so feel free to say I'm done.
No, that's okay. If there's any more burning questions, I'll take them, but I'll have to go soon. Otherwise, my husband will die of starvation. It's tea time.
All right, Dietmar. Go ahead, Dietmar.
Well, thank you very much, Dr. Thomas, and sorry for the late question.
That's
but
fine.
I did get from your last answer. In hospitals, we treat patients that have cancer with radiation and
You're
possibly
breaking
other
up.
diseases
You're
too.
breaking up quite a bit.
The usual. What about the radiation doses cancer patients are getting in treatment? Are they being studied to see low dose and the doses anyway that people are getting in hospitals for treatment?
Yeah, there are loads and loads and loads of studies. There are huge numbers of people enrolled in and there's a European study. I think there's also a US study looking at CT and late effects. The problem with anything when you look at it for treatment in medicine is somebody has come in who is sick. Their body is not right. So you start off with a cohort of people who are not normal, if you like. So you have to be really careful that what you're actually noticing in that cohort is related to the radiation dose you've given them rather than any other underlying condition. So they're extremely difficult studies to do. You have to have large numbers of people in them and they have to be rigorously controlled. But there are large numbers of studies going into this. There's lots of studies, for example, where people have had radioiodine for thyroid treatment. To look whether there was any effect on any other tissue, because the salivary gland takes up iodine but doesn't store it. Obviously it passes through your body but doesn't get stored anywhere other than in the thyroid. And once your thyroid is removed, obviously your storage is gone, so it could get elsewhere in the body. And again, you see very few people coming back with anything above the normal rate of cancer that you would see in that population. And again, because they've had one cancer, you don't know whether there's something lurking in the genetics that makes them more predisposed. So they're extremely difficult things to do unless you have a massive effect. If you had a massive effect, these studies would be really easy because you'd see it very quickly. But because we're looking at something that is a minuscule effect on health, and therefore can get disturbed, you're looking for the needle in the haystack, really, can get disturbed by all the other things that have an effect on the health as you get older. It's extremely difficult to quantify that accurately. There may be a risk. If there's a risk, it's a very small risk. And if I had a child who needed a CT, for example, I would say do the CT, because if I'm advised by a doctor that my child needs a CT, they're doing that because there's a worry about the child that they need to sort out, which could result in death or morbidity or whatever. So I would never refuse that. And I've had my own son, when all of this was happening, he went in and having hurt himself on the football field, and he was adamant he didn't want an X-ray because he was worried about his genitals. And you sort of have to sit down and say, no, don't worry, they're doing your foot. It's nowhere near anything else. And the dose is very, very small. So unfortunately, when we talk a lot about this, we actually cause problems in hospitals because we're actually making people frightened of any form of radiation for any reason. And if a doctor tells you need a test, particularly in this country where we're very tight with money and it comes to healthcare, you have it done because there's a good reason for needing it.
Thank you so much, Dr. Thomas, for taking the extra time to answer questions and everything. And I'll just remind everybody that the recording will be posted to the Southeast CCL YouTube channel. And if you're part of CCL, please go ahead and click on the link and record your attendance in this meeting. I appreciate you so much. Salami, is there any other closing words?